Okay. Yeah, so can you guys hear me okay?
Yes, we can hear you.
And so, yeah, this is now time for something completely abstract. I'll start my slideshow. So I'm calling this talk Moby Dicky. It's basically a whale story. It's a white whale story. And I'll describe some research that I've been doing over the past year in the Kaluza theory under a cooperative agreement with DARPA. Now, actually, those of you who might remember, in 2016, there was a talk on the Kaluza theory at the 2016 Estes Park meeting. But, and at that time, when I co-organized the meeting with Jim and Hal, I'm sorry, Heidi at the time, I had the idea that there were two good ideas that I had encountered for a breakthrough in propulsion. One of them was the gravitational inertial induction stuff that Jim and Hal are working on. The other one was this Kaluza theory. But in the event, it turned out there was a lot more interest in the inertial induction, the Mach effect stuff. And I think the talk was recorded, but what I'm happy to report is that I took that seed idea of two basic ideas with a breakthrough in propulsion, the theories are known, to see if there was some sort of exotic propulsion phenomena in laws of physics that we're sort of already aware of. And so I'm pleased to find that actually in the Kaluza theory, we did find something big. So you can say goodbye to Machian micronewtons and say hello to Kaluza kilotons. But unfortunately, there's an asterisk. Yes, there is an asterisk. And these Kaluza kilotons are probably too big to be true. And I'll get into the details of how these forces, these apparent forces, manifest. But basically, they involve electrostatic experiments. And just informally talking with George Hathaway, Martin Timar, they don't see these type of forces anecdotally. So we don't expect to find them. And so we have a bit of a puzzle here. And so this is the whale story. So just to summarize, I am working a 2-year cooperative agreement with DARPA to look at two possible avenues to a breakthrough in propulsion. And the first one is this Kaluza effort. And so I wanted to explore if the known laws of gravity, and by here I mean the Kaluza theory because the laws have been known, the mathematical laws have been known for a century. I wanted to investigate this electromagnetic control, possible electromagnetic control of gravitational coupling in the Kaluza scalar-tensor theory. And lo and behold, yes, at least in the theory, mathematically, there are large apparent forces in this theory. So the work that I'm going to present now over the next few minutes is summarized mathematically in a series of 3 papers. So I'm not going to try and derive results. I will report results, and I will refer to these papers for the mathematics, although I would be glad to talk about it, talk about some of these results. But I'm comfortable that the mathematics are described in detail in these 3 papers. Now, the first one was from 2015, and really it was the paper that led me to go on to develop the proposal for DARPA. In this 2015 paper, I looked at the field equations in the Kaluza theory, just the 3 force fields. And then during the course of my effort with DARPA this year, I put together a body of work and investigated the matter sources and the energy momentum tensor in the Kaluza theory. It turned out there wasn't a lot of work on this, although Kaluza himself considered matter sources. But in the second paper, I feel like I completed the mathematical theory. There's really nothing new in here. In these 2 papers, you can find it throughout the literature. It's just more coherently written in these 2 papers. And then I have this third paper, which I'm currently submitting for peer review. This one describes the long-range scalar forces that I've calculated in the framework of this theory. and that I will be reporting to you today. And that one is on the archive preprint server if you want to take a look at it. So those three papers summarize mathematically everything I'll be reporting today. Now, just a bit of Kaluza history, history of the theory. It's sort of interesting. As we know, Einstein discovered the field equations and Hilbert in the same year, 1915. They discovered the field equations of general relativity. And a few years later, in 1919, Einstein got the manuscript from Kaluza, which pointed out that if you write general relativity in 5 dimensions, you can recover classical electromagnetism along with standard 4D general relativity. A few years after that, in 1926, Klein gave his quantum interpretation to the Kaluza theory, and Klein interpreted this 5th dimension as a wrapped up, compact, microscopic dimension, which we've known ever since. Klein's paper influenced quantum field theory profoundly. And at that point, the classical Kaluza field theory was abandoned. So it was discovered in 1919. It was abandoned in 1926 with the heat of the quantum revolution. Now, there's a scalar field in this theory that Kaluza did not address. I'll get into the details in a moment, but the scalar field equations were not developed for decades after the 1940s into the early 1960s, and it was all done by groups in Europe. Now, the foundational work by Robert Dicke, and that's where we're getting Moby Dickey. The foundational work by Robert Dicke on tensor gravity was in the late 1950s and the early 1960s, and he worked out what the implications of a scalar field, a long-range scalar field, would be. Then I call it a renaissance in classical Kaluza theory, 1980 to 2000. Many basic results were established, so there's a very rich literature on all of this. I will note that this classical Kaluza theory that I'm reporting is not viewed as fundamental physics by APS or the American Physical Society or the National Science Foundation. Engineering implications not of interest. It's this sort of high-risk thing that is of interest to DARPA, and that's why I'm investigating under a DARPA agreement. So the theory I'm going to report is scalar tensor gravity. That's sort of what it's known in the zoology. It means that there's a scalar field which couples to matter in addition to the metric, in addition to the gravitational field. And it turns out people have done a lot of work experimenting observationally and theoretically with extensions to general relativity. The scalar field extensions remain mathematically viable. They are not ruled out in the classic, campaign of tests in theory in the 1970s and 1980s. So another weird thing, interesting thing about these scalar tensor theories, is the scalar field is interpreted as a variable gravitational constant. So the Kaluza theory is a scalar tensor theory. What makes it unique is it has electromagnetic couplings in the scalar. And now we come to Robert Dicke. He had a series of classic papers on long-range scalar fields and extensions to general relativity. And it's been a profound resource for my work of the past year. I've gone back to Dicke's papers again and again. And Dicke felt, as I do, that there should be a scalar field out there. It's the simplest of the 3 massless bosons. And so that's why I've decided to call this Moby Dickey. So let's look at what Dicke was talking about. If you just think about the laws of relativity and you think about classical fields, there's only 3 possible types of classical fields: scalar, vector, and tensor. And I've written them each here to put into the framework where the scalar field fits. And it does seem very abstract, but the way we define these fields is how they look in certain coordinate systems and under coordinate transformations. A coordinate system is just a set of yardsticks and time clocks to measure time and distance. make measurements and compare against theory. It's a fundamental tenet of physics that physics does not depend on your coordinate system. God did not choose a coordinate system for us in which physics holds and other coordinate systems in which it doesn't. So the fact that the coordinate system doesn't matter allows us to identify in classical field theory 3 types of fields. The scalar field is one that is the same in all coordinate systems, and that's what the prime indicates. I'm writing the field in the prime coordinate system equals the field in the unprimed system. When we consider the next most complicated classical field, that's the vector field. And this one has a relation between the prime and the unprimed frames given by that derivative of the coordinates. We don't need to worry about what that is. But the main point is that when we look at the tensor fields, its transformation is a product of those, of what we saw in the vector. And so we get an idea of how these fields go. We get powers of this coordinate transformation. Dickey did address whether there would be tensors higher than rank 3 in nature. And he used the word, that God would not be so malicious as to prescribe a 3rd rank tensor. At least we have no evidence for one. So these are the 3 mathematical allowed fields in classical physics, and by extension, the allowed fields in nature. Now, we've identified 2 of the 3. One of them, the vector field, has been found. It's electromagnetism, and its massless boson is the photon. All of the classical fields are thought to correspond to massless bosons if you go to a quantum limit. I will not mention quantum stuff except right here on this slide. This is a classical theory, but Dickey spoke in terms of massless bosons. It's always the subtext. So we did find the vector field in nature. It is electromagnetism. We found its massless boson. It's the photon. We also found the tensor field in nature. We found it is the gravitational field. So the gravitational field is our tensor field. Its massless boson has not been found. It's the graviton. Everyone's heard of the graviton. No one's ever seen one. And there are reasons that we shouldn't, but I think it's sort of intriguing that we have a classical field everyone knows should exist, or does exist, I'm sorry, it does exist, and it has no observed quantum particle. So back to the scalar field, it's missing. This is our whale. We have not found a scalar field in nature, a long-range scalar field, to go along with gravity and electromagnetism. The scalar fields are invoked for various things. There's the Higgs boson. None of those are this. We are still looking for the classical long-range scalar field. So I would like to now give you some of the detail on how the scalar field fits into the overall laws of gravity and electromagnetism in the Kaluza picture. And it is quite compelling. So the idea, as I mentioned at the top, as Kaluza realized, is to just write gravity in 5 dimensions, write general relativity in 5 dimensions. And what I've written here, the tilde GAB, is obviously it's a 5x5 matrix. That is our 5-dimensional gravitational field. It's a 5x5, it's symmetric. So there's 15 potentials here. There's 15 independent numbers in our 5-dimensional gravitational field. And this is written schematically. It's not exact. That's why I put the similarity symbol. I didn't want to obscure it with other confusing factors. I want to give you the basic idea for how gravity, electromagnetism, and the scalar field are wrapped together. And you can see the purple highlighted area is the gravitational field in this picture. It's a subset of the 5x5. The 4x4 subset is the gravitational field of general relativity. The vector components here, the 4 vector components, are the electromagnetic field. And when you play this game, you have a 5 by 5, you have 15 potentials. Gravity and electromagnetism only make 14. We have one more free potential, this corner potential here. It has no analog in known physics, but if this picture is correct, it's implicated. It seems it must exist if this picture is correct. And so that's what I call also the dog that didn't bark. It seems malicious that you could have this picture that works perfectly for gravity electromagnetism, but there's no corner potential. I find that hard to believe. So anyway, moving on. So the way we proceed, when we get into the field equations for this 5-dimensional gravitational field, they also break out in a matrix form. And our gravitational field equations are going to be 10 equations, and our electromagnetic field equations are going to be 4 equations in the 4 unknowns. And then we're going to have a scalar field equation, and we can arrange them in a matrix just like we did the gravitational field. And so here it is. This is really the whole Kaluza theory in a nutshell in one slide. You can see in the upper left, there's the 5-dimensional gravitational field broken out in terms of the 3 4-dimensional fields. On the right-hand side, upper right, you can see the field equations, the Einstein equations in 5 dimensions. Below that, the derivative of the fields with respect to the 5th coordinate is 0. That's a key part of the Kaluza picture. It has its own name. It's called the cylinder condition. And then there's a constant in the Kaluza picture that I've written there, sort of an electrogravitic constant. You can see it involves the gravitational constant and the permittivity of free space, which is the electrical constant. And then in the bottom row, I've sort of written out the field equations, broke them into their parts, and there is a set of Einstein's equations with a scalar field energy momentum and with electromagnetic energy momentum that is driven by matter sources. We can see Maxwell's equations with the scalar field invoked there, proportional to currents. And then in the corner in the lower right on the left-hand side, lower left, is the scalar field equation. And it's an oddball. It's known, it's in the literature, and it does implicate the electromagnetic field with the scalar field. And then the source of the scalar field is a bit of a mystery. There's not good literature on it, and that's the one area where I've tried to do some original work and take a shot at what this thing must look like. So, with all of that set, here is the problem that I proposed to DARPA, that I proposed to look at as why this theory was interesting. Because we've just agreed that we have a Kaluza theory, we have a theory, we think, where the gravitational constant is a variable and it couples to electromagnetism. Can we control the gravitational constant locally and electromagnetically and affect Newton's law of gravity? And I've written Newton's law of gravity there. I've divided out the mass on each side. This is, as we know, it's an equivalence principle thing. But the basic question is, can I use my electromagnetic Kaluza chicanery to fiddle with the gravitational constant and reduce locally gravity? And the reason I'm raising this is actually the answer is no. And I wanted to do it because this is initially what I proposed, and I realize now it's naive, and I realize other people might think in this way. And so I wanted to spell out why this didn't work before I get to what I think does work. So why can't you do this? Well, the easiest way to see it is to look at the Lagrangian. I know not everyone are mathematicians here, but the laws of physics are always summarized with a Lagrangian. Every known law of physics that's accepted has a Lagrangian. And a Lagrangian is a scalar. It's one number at every point in space and time. So there's no 10 components, 4 components, vectors, tensors, none of that. It's just one number. Now you can see it's written in terms of tensors, but it is quite simple. And what I've written here is the Kaluza field Lagrangian, and I've highlighted how the scalar field comes in. If we set the scalar field to 1, we recover classical physics. We recover normal electromagnetism and gravity. But what you notice here in the Lagrangian, the term on the left is the gravitational piece. And you can see that it involves the gravitational constant. The term on the right is the electromagnetic piece, and it involves mu naught, which is the permeability of free space. It's the electrical constant. So the point is, in the Lagrangian, the fields have their own constant wrapped up with them. So the gravitational constant is not a coupling constant between matter and gravity, as it looks in Newton's law of gravity. It's actually a property of space-time. It's sometimes called the stiffness of space-time. And so the gravitational constant is telling you how much curvature you get for a given amount of mass energy. It's not a local coupling constant. So I think that is why the initial idea was flawed, that you could locally adjust the force of gravity. And I think the flaw is to think of your gravitational constant as a coupling constant to matter. It's not. It's a field thing. So moving on, I think I'm good on time. Cosmological implications. So in Dickey's famous theory, the Bronson-Dickey theory, they show how the scalar field can be understood as a gravitational constant, and they quantify it by Dickey posits a field equation. He says there's only one possible covariant scalar field equation, and that's where the covariant D'Alembert of the scalar field, which is this thing on the left in the top equation, is equal to the mass density, the energy density of the universe. And so that's the first term on the right. That was Dickey's equation. What we have different is a magnetic field piece here. That was not in Dickey's picture. And if we solve this equation, or take a different route, we're not looking at length scales like Dickey did to identify this as the scalar or as a gravitational constant. Instead, we find that there's a 0 in this equation. And there's a critical ratio. The gravitational constant can be understood as a ratio between the mass energy of the universe and a galactic magnetic field. Now, the divergence of the magnetic field is still 0. There are no sources. So when I talk about a galactic magnetic field, I'm thinking like domains. We know that all the galaxies have magnetic fields, huge magnetic fields that extend, thousands of kiloparsecs into space. And then the galaxies are in clusters, and there's huge magnetic fields around those clusters. So there is magnetic field in intergalactic space, but it's not treated in the cosmological energy budget. The standard cosmology, lambda, cold dark matter, treats dark energy, dark matter, visible matter, neutrinos, and electromagnetic radiation. There's no bulk magnetic fields in those energy budgets. And I find that indeed this magnetic field is below the energy budget of the cosmic microwave background radiation, so it seems okay. And when I plug these parameters in, when I use a normal value of the intergalactic magnetic field strength, I get a number similar to 1. And if I look at how these two things depend on the cosmic scale factor, I know I haven't explained what that is, but some of you know what it is, the cosmic scale factor A. You can see that this scalar field has a very weak dependence to the power 1/3 on the cosmic scale factor. So again, this was all lining up, and I actually did not publish any of the cosmological considerations in any of those 3 papers. So this is all new stuff. This was sanity check to see at the cosmological level, is this behaving okay? Is it really giving me a variable gravitational constant, but not too variable? Because we have limits on the variation of the gravitational constant. If the gravitational constant varies by too much, then nucleosynthesis is enhanced or degraded, and you don't get the right abundances of the light elements with the Big Bang. So you can't just mess around with the gravitational constant and mess with it any which way. You can allow some variation, but cosmologically it has to be weak. And indeed, the Kaluza theory without any forcing it's okay. It's behaving okay. I'm getting the right magnitude for the gravitational constant. It's not strongly varying. And I get this bonus prediction of a primordial magnetic field. So this to me was really compelling when I did the cosmological stuff first before I even got into the scalar forces because I felt it was important to convince myself that this thing is hanging together as a variable gravitational constant. Okay, enough said. So now let's come into the real heart of it. This is the force equation in the Kaluza picture. And if those of you who know the force equation in general relativity, it's called the geodesic equation. This is the geodesic equation in 5 dimensions. And I have obviously highlighted the 3 forces here. The stuff on the left-hand side is standard gravity, standard general relativity. The stuff in the middle, whoops, let me go back, is electromagnetism. And the stuff on the right is the new stuff. That's the scalar force. And it's sort of an oddball thing. This force equation gives this is what's giving us our large force effects. Now there's no free parameters. I couldn't set anything to 0. Everything is scaled. There's no free parameters. I'll say with an asterisk again, but at this level, I haven't found a way to tune this away. So if you see, the gravitational constant is in the denominator in that scalar force. So you can kind of see why this might be large. And in fact, it is large. The other weird thing, which Dickey noticed about scalar forces, is that they accelerate at constant energy. And ever since I read that, it's been hard to wrap my head around it. But now I do see it in the mathematics here, but it challenges my intuition for what this really means. But you can see that strange sort of subtraction on the scalar force term, the metric minus the 4 velocity. That's a projection operator, and it is projecting off the component of the gradient of the scalar field that's perpendicular to the 4 velocity. So again, it's another way of saying that the scalar force accelerates at constant energy. You could also say, well, I want to set time derivatives to 0. Look at steady state, and then if the time component is 0, but I've got spatial gradients, again, I'm accelerating at constant energy. So from a relativistic perspective or unrelativistic, non-relativistic, we've got some weird behaviors here that I don't think we've seen in normal physics, and it's hard to contextualize them. Okay, so now let's get into the new stuff. This slide here, scalar charge and field. This is all new stuff, and this is in that last. Yes, go ahead.
This is Sunny. Could I ask a question here, or is it going to mess up your story?
No, I think we're good on time, Sunny. Yeah, go ahead.
If you could just go back 1 slide.
Mm-hmm.
So you said you intimated that because you have this c to the 4th over g, that this pink scalar force is going to necessarily be large. Am I reading you correctly on that?
The coefficient, yes, if assuming the gradients are not 0.
Oh, I was going to say that was going to be my next question. Even though that first term might be huge, maybe that just is an indication of what could be realizable in terms of the gradient of the scalar field.
Right, and for a long time I thought that that's what was going on, but then I found gradients, and so yeah, and I'll get into that. We'll quantify it a little closer, I think, which will shed some more light on what you're asking about.
Okay, thanks.
Yeah. Okay, so So I want to emphasize this is the main new discovery on this slide, the identification of scalar charge. And in that third paper, I go into this in detail, but gravity has a charge, which is mass energy. And electromagnetism has a charge, which we know, electric charge. Here's the scalar charge. Here's the charge for the scalar force. And you can see I've written it. It has, well, you can't, it's hard to tell, but you can take my word for it. It has units of energy. And that whole thing on the left is just units of mass. So we've sort of got an MC squared here. That's the scalar charge. And again, there's G in the denominator. That's why it gets big. Now, another thing that I've done with the Kaluza scalar field, which I think is new or relatively new, is to treat the scalar field as a perturbation. We already discussed how standard physics is obtained when the scalar field is 1. And we discussed how cosmology, or I claim cosmology, appears to set the scalar field to 1. So in that way, it's very much like the Minkowski metric. This component, this scalar field, we know it's in the corner piece of the metric. So I did a perturbation calculation treating the scalar field like gravity, just like we do for the Newtonian limit of gravity. We do a perturbation around Minkowski. That's exactly what I did here. And that's what Dickey did. But in the 80s, in that renaissance of Kaluza, no, that whole scalar field perturbation thing was lost. And so I think I'm bringing it back again from the Dickey era. And here is my scalar field potential. So this is the equivalent of GM over R, or you know what the Coulomb potential is. Here is the scalar potential. New to physics. Never seen it before. The same with the scalar charge. So again, these are really interesting results. I just don't know what to make of them. And even more exciting to me with all that, you know, we had the primordial magnetic field, we had the scalar charge. We get a third new length scale of physics for a massive charged body. And I've written all 3 of them there. 2 of them were already known from the Reisner-Nordstrom metric. The Reisner-Nordstrom metric is an exact solution to the equations of general relativity for a charged massive object, electrically charged. And it solves the combined Einstein equations and Maxwell equations. And if you look at the Reisner-Nordstrom solution, you can see there's 2 length scales. There's a length scale from the mass of the body and a length scale from the charge. And what we found, what I found, this third Kaluza length scale is from the scalar charge. So we had a length scale from gravity, we had a length scale from the electric field. Now we have a length scale from the scalar charge. And this is a new length scale in physics. And I thought all the length scales in physics were already found and named. I didn't think there were any more. And so I was really stunned by this. I wonder, are there a bunch of these more? Can anyone just stumble across a new length scale in physics? I don't know. But now I'm keeping score on new length scales in physics this year. Confluence Research 1, Princeton 0. So I think these are interesting results, and I won't brag anymore. There's also an effect of scalar radiation in these field equations. And now this quantity C on the left-hand side, that's our perturbation. So it's not the scalar field itself, it's a wave in the perturbation of the scalar field. The first term on the right-hand side is Dickey's source term, which just depends on mass energy. The third term on the right-hand side has long been known in the Kaluza theory. It's long been known that electromagnetic fields, as written there, are sources for these scalar waves. But the new piece is that Q squared. Again, I examined the sources, and I've added a third source term to this scalar wave equation. And so I'm, thinking if you actually saw one of these, or if they existed, it might behave like a scalar electromagnetic wave, which is an oxymoron. Although people talk about it, I think you have to get precise about the mathematics. Also, the fact that it is a scalar, it might behave like a sound wave, like a longitudinal wave, and it might be deep penetrating like a gravitational wave. So as we might expect, this theory that mixes gravity, electromagnetism, and scalars has a wave mode that might mix aspects of these. So this is all speculative on my part. I don't really know. All I know is that equation that's written there. So still doing good on time. So now here I'm going to come back and answer Sunny's question. And I've put it, I've got a busy diagram here. So I'm looking at the scalar force and the gravitational force around a planet with some mass. So the blue circle is a planet. In the problem, I have mass, I have gravity, I have scalar field. There's no electric field. And now on the left-hand side, I've evaluated the force equation using the geodesic equation we looked at earlier. And I've written the gravitational force and the scalar force side by side. So I'm going to point out a few things. The first thing is that gravity is a well. We know that gravity sucks things in. The scalar force is a hill. It pushes things out. And I wrestled with the sign on the scalar field a lot. I feel confident I've got the sign right, but you know, one never knows. But this is the picture that I have so far. Now, what's also interesting is that I've written it in terms of coupling constant times gradient of the potential, because that's how forces are. So we can compare. And the really interesting thing is that the gravitational potential and the scalar potential are basically the same, GM over RC squared. So what's different is the coupling constant. And of course, there's a factor of 3. I'm not worried about the factor of 3. You know, the basic scaling is GM over RC squared, but the coupling constant is different. And so it's showing that an electrically charged object should feel a repulsive force from the planet. And that is the big force. When you put in these numbers, these are the Kaluza kilotons. This is what George Hathaway and Martin say they've looked for, and they've never seen any sign of that.
Sorry, may I ask a question?
But this, yeah, please do.
Like you introduced the scales, right? So you introduced a new scale. Suppose, but this is for Reisner-Nordstrom. It's like black hole which doesn't rotate. Suppose you have some Kerr matrix, right? In Kerr matrix, you also have J, so angular momentum, right? So if you have a Kerr matrix, doesn't mean that you will have some additional scale. So roughly,
well, I mean, this calculation is just spherically symmetric. You know, there's not assumed to be a broken symmetry along run direction like a Kerr metric. If one was to investigate that, we just have to do another calculation.
Okay.
Yeah, thank you. Yeah, so I think, Sunny, I think this gets to what you're saying, that, or you were asking about, is the gradient small? And what's really interesting, what I've learned from this, is that the gradient of the gravitational field is small. If you do GM over RC squared at the surface of the Earth, it's 10 to the minus 10. It's minuscule. The gravitational potential of the surface of the Earth is almost 0. Yet, it's a big engineering force. It causes trouble. And why? Because for gravity, it's mc squared. So even though the gravitational force is 10 to the minus 10 at the surface of the Earth, the coupling is huge with mc squared. And so you get reasonable forces. So that's why that argument, Sunny, I used to have that argument. I used to think, well, the gradient must be 0. But now I realize that when you're talking gravity, your potentials are 10 to the minus 10, and you still have big forces. So you really have to be careful. And like I said, now I'm living with these large forces from minuscule potentials, which we all already live with normal gravity. Okay, now what about atomic
Thanks, Lance, for
scales?
highlighting that. I appreciate that.
Yeah, was that you, Sonny?
Yeah, I appreciate you closing the loop on that. That's useful.
Yeah, thank you. So I looked at the force atomic scales because obviously, we can't mess with hyperfine splitting or, we know all the energy levels of all the atoms. So, and everything is known to 13 significant figures when we get to the atom. So the question is, what does this mean for atomic physics? Is it breaking atomic physics along with these stupidly large Kaluza kilotons? Well, scalar and gravitational force become proportional to electric charge. So when you look at these couplings at the atomic level, where you've got 10 to the minus 19 coulombs in 10 to the minus 24 kilograms, it's a huge charge to mass ratio, and things start to merge, and the scalar and the gravitational electric forces all become proportional to electric charge. It's like they become one force at the scale of the atom. And so I find that the scalar force masquerades as the electric force at the atomic level. Again, I've stolen this concept from Dickey. Dickey described how the scalar force would masquerade as gravity and would be very difficult to measure. With the Kaluza theory, I'm finding there's electrical masquerading in addition to gravitational masquerading. So I'm coming to the end. Two more slides, and that'll leave plenty of time for questions. So squelching the coupling. The predicted forces seem unrealistically large. The predicted scalar field at magnitude matches cosmological constraints. And an undiscovered scalar field seems likely to exist, at least based on the arguments we started the discussion with. So what's wrong? I think perhaps I have an error. It's hard for me to believe the theory is wrong and that I've nullified it, although ostensibly that's what's happening. But my sense, my gut is telling me that I've made a mistake in the coupling. Something is not right. If I sharpen my pencil and redid the calculation, I should get a minuscule scalar force, and I'm not doing something right. But it doesn't mean that the scalar field's not there. So I'm looking for a way to squelch this apparently strong coupling, or maybe correct my error if it's there. And I think that if we could understand it, if we could make the final leap to understanding and find a way to squelch it, then maybe we would really have mastery of the scalar field, and we could find testable effects, that are something that would be a new effect and testable, and not just these absurdly large Kaluza kilotons. So we did add a milestone for this project for a simple test. And in light of the predicted large forces and the importance and the simplicity,
Check.
I went to DARPA and noted that for a very small increment of funding, like the sort of amount that might shake free in any large organization with lots of things going on, we could actually just do a simple validation test to test this thing. And the original concept was that I would work through the Kaluza theory. If I did find something, I thought it would be small, I would deliver a design for an experiment. Well, instead, I found something very big, very simple. And that caused me to go back to DARPA and suggest that we mount a simple test, even in light of what George Hathaway says, even in light of what Martin Tamar says. So that funding has been approved and an experiment designed. We are working with Hathaway, and we have the statement of work was approved between me and Hathaway and between me and DARPA, but we are still pending funding. So we've done some calibration work in George's lab, or George has. Obviously, because of the pandemic, I haven't been able to travel as I intended to sort of witness some of the preparation work as well as the execution. So we're cautiously pessimistic this won't work, but the idea that we're spending a little bit of money just to make sure, I think is indicative to me of how important these results are.
Lance, can you hear me?
Yes, I do. Who is that?
This is Greg from Aerospace. I was having trouble getting my microphone to work.
I hear you loud and clear. Yeah, go ahead.
Yeah, thank you. Back when you were showing about, when you mentioned that charged particles might be gravitationally repelled, right?
Right.
What about the solar wind, which is exactly charged particles heading towards the Earth? Is there any evidence that they're following that same kind of repulsive path?
You know, I hadn't thought about the solar wind, but I actually started my research career as a solar wind researcher. So I think I understand the acceleration of the solar wind. In fact, I wrote papers on it. But, you know, you're right. Maybe I should go back and think about that again. Maybe it's a way to falsify all of this, or maybe it has some light to shed. So thank you for the comment.
Sure.
Okay. So milestone 4, so conclusions. I think the task 1 project was a success in that, you know, we wanted to prevent surprise, and there was a surprise to be prevented. You know, there were big forces there, and I've written them up in those 3 papers with the hope that someone will tell me what I did wrong. Those forces are so large as to nullify the Kaluza theory. But this would be the first nullification. Otherwise, I thought the classical theory was perfect in its, you know, match to 4D physics. So again, I suspect I might be doing something wrong in the coupling. So that's kind of my takeaway. I am not ready to say that the theory is wrong. I'm not ready to say that the scalar field is not there. I'm only ready to say that maybe I did something wrong. But if I don't find out what that is, then it would stand, I think, as a nullification of this Kaluza framework. So, yeah, further work to find a mechanism to squelch the coupling. So I think that's it. I'll stop there, Hal, and maybe give us a little extra time for a break.
Oh, well, thank you very much, Lance. In fact, are there any questions? Maybe we should open this up to questions, and we do have at least just over 10 minutes even.
Yeah, it's George here. Lance, when you're talking about length scales, for the engineer, can you describe the physical representation of these length scales?
Yes, let me just pull up the slide, this slide here.
Yes, sir.
Yeah, it's just a mathematical, how can I say it? You know, the gravitational potentials are unitless. And so if you go out some distance, you know, there's a length scale made of constants multiplying or dividing the length scale of distance. So I feel like I'm struggling to explain it, but, you know, there are only certain ways to get, you know, to arrange physical constants to find length scales. For example, like the Planck length, they would say that gravity is at the Planck length. You know, so whenever you have a physical problem, you take the parameters and you combine them, and you can make time scales or length scales, which will govern the dynamics of the system. So when you see a length scale, George, like when you have a charged sphere in your lab, I mean, the length scale is how fast the electric field falls off.
Right, that's what I'm wondering.
Yeah. So.
Thank you.
Hey, Lance, this is Max from Aerospace. Can you hear me?
Hi, Max. I hear you
Hey.
fine.
Great. So you mentioned the cosmology, and I was wondering if you looked at it like in terms of the sort of the energy budget of the universe, because the data sort of gives you a scale for dark energy and how much is supposed to be there, if you thought about that at all.
Yeah, I mean, I did go through all of that. One thing I didn't, I parameterized all the dark energy and the matter as like a mass density. So in my notes, I wanted to go back and treat dark energy properly, you know, as obeying a vacuum energy equation of state and all that stuff. But I think this this formula, this wave equation, or this cosmological equation that kind of gives the gravitational constant in terms of the mass density and the magnetic field, I believe it's going to be robust. I don't think if I treat the dark energy better, it's going to fundamentally alter this result. That's my expectation.
Okay, cool. Thank you. And one more question. You mentioned the scalar waves. If you thought at all about how to generate them, what kind of scales would be involved, what they'd look like, etc., what kind of effects you'd see.
Yeah, this is it. This is all I have. I have the wave equation. And as I said, you know, this wave equation's been known for a long time in Kaluza theory. I've put the matter sources in. And so, and again, you pick up Dickey's source, but I don't know what it means. You know, nothing's time dependent there. If you look at a wave equation for electromagnetism, I believe it's like in gradients of the charge density and time derivatives of the current and stuff like that. I don't know. And maybe a careful analysis of the length scales here, you'd say it just can't wave fast enough. Like the wave frequency is 1,000,000 years or something. The period's 1,000,000 years. I haven't done that analysis. So maybe we should hold off thinking that this might imply like optical frequency waves.
Okay, got you.
Are there any other questions?
Yes, we have one. If you were to take two electromagnetic waves, which are traveling, so they have their vector potentials traveling with them, and they're carrying a certain amount of energy, a mass equivalent energy, you could say, but because they have their light speed velocity, we don't really observe that as mass. If you intersect two of these waves where you nullify out in a given volume of three-dimensional space the electric and magnetic potentials so that they're effectively destructive, but the energy in the waves is still contained in that volumetric space, if these two waves effectively cancel each other at this point space within the wavelength of the two intersecting waves, and then they exit the other sides and still have all their energy, in that tiny space, wouldn't that create a scalar potential that could be measurable or maybe even have influence on other things? I'm trying to find a way to do this in a testable fashion.
Yeah, I'm not sure. Even, you know, what you described is a bit of a paradox. Like, you know, two particles, they have, you know, a photon has energy, but if you conspire them to add up to zero, what happens to the energy? That's a bit of a paradox.
Exactly. I mean,
but I was going to say, if I could, I'll just make one point on this F term. You know, this source term that's long been known. It's a Lorentz invariant it's electromagnetic.
Exactly.
A Lorentz invariant. This thing is zero for electromagnetic waves. So I think this is really interesting too, that electromagnetic waves are excluded from the party here. Yeah, it has to be a bulk electric field or a bulk magnetic field.
So that would be like the H field, the phase conjugate field from all the charges?
Well, this is my primordial intergalactic magnetic field, let's say, or you know, at the cosmological level, but it appears that the sources for these scalar waves are not electromagnetic waves, but bulk electric or magnetic fields.
Okay. That makes a little more sense.
Yeah, just because this F is zero for electromagnetic waves. So it's like the electromagnetic field has like a chaperone effect for the scalar field. It's always kind of tied with the scalar field, but it doesn't come into the energy budgets. And if you think about it, the energy momentum tensor for electromagnetic fields, the trace is zero. You know, we don't worry about the trace so much, but it becomes important here. So the electromagnetic stuff keeps dropping out with the trace. There's a strange relationship between the scalar and the electromagnetic in this thing.
Yeah, that's very interesting. I'd love to have a chance to talk with you on this too after the conference, because I have a few ideas of like maybe you can help you.
Yeah, I think we've chatted before, and you know how to get a hold of me. So And take a look at that third paper. It's got a lot of this in there. Yeah.
Looking forward to it. Thank you very much, Lance.
Thanks, Max. Yeah.
Okay, we still have 5 minutes. If you like, we could have a break for 5 minutes. Start again at 11.
Yeah, I'll stop sharing. Thanks again, Hal, for organizing this and pulling it all together. I know it's a lot of work. Thank you.
There's no problem.